So, we will discuss now about exclusive OR gate operation, truth table and its symbol, the logic circuit of XOR gate. So, what is XOR gate? It is also called as exclusive OR gate. So, XOR gate has I output if either one of or other inputs are I but not both. So, you can see here the truth table of XOR gate. So, we have two input XOR gate. For two inputs, as you know, 2 power n combinations can be generated. So, 2 power 2 we are generating 4 combinations. Alright. So, here we can see here 4 combinations. So, this is the output of XOR gate. So, the output is I if and only if either of the inputs are I. If both the inputs are low, your output is 0. If both the inputs are I, output is 0. So, you are going to get output I if and only if either of the inputs are I, but not both. Both need not be I and both need not be low. So, either of the inputs are I, then my output will be logic I. So, writing an equation for this truth table. So, considering only the logic 1 at the output side, you can just see to logic 1 at the output side. So, corresponding inputs, this is A complement B. For this, it is A B complement. So, final expression for XOR gate is A complement B plus A complement B plus A B complement. So, you can just see here A complement B plus B complement. So, we are going to generate XOR operation. So, how to write the circuit, logic circuit and symbol for this XOR function. So, as I said, we have two inputs A, B. So, we have NOT gates to generate the complement. So, we have A complement B, A B complement and A complement B. So, my output is the summation of A B complement and A complement B. So, I am generating A and B complement here. This is one AND gate, this is another AND gate, 2 AND gates and 1 OR gate. I am going to generate this equation. So, this equation is finally consists of 2 AND gates and 1 OR gate. So, this is the logic circuit for XOR gate. So, in general, I can write this is a basic symbol of XOR gate A B. So, this is the XOR symbol which represents, this is actually a symbol of XOR. So, this is how I am going to write the equation. So, this represents A XOR B and this is the equation. So, we call this as 2 input XOR gate. Similarly, I may have more than 2 inputs. So, A XOR B, I can XOR the same function with another input. So, this forms A XOR B. Once again, it is XORed with the another input, that is C. Similarly, the other way around, I can XOR B and C, that is XORed with A. So, we can generate multiple input XOR combinations. So, need not be only 2. So, I can have many input XOR gates. So, we will discuss about parity generator and checker. So, what exactly the parity generator and checker, where is the requirement, what is the requirement of this, where exactly we are using this parity generation and checking. So, whenever we transmit some bits in the transmission line, there will be an additional noise called electrical noise. This electrical noise in the transmission of the binary information can cause errors. So, whenever I send in binary information, definitely because of the noise, there will be an error. Your original bits may be transformed or changed. So for that we need to detect or check these type of errors. So whenever I send a original bit, the original bit may be corrupted and may be altered due to noise. So for that we need to detect the errors. So we call parity. We add an extra bit we call as parity bit to detect these types of errors. So we have to develop systems to detect these types of errors. So we have two types of systems over here. One is odd parity, the other is even parity. So what exactly this parity is? It is nothing but an adds a bit to the binary information. So to your original information, I am going to add an extra bit. So this extra bit is called as parity bit. So either I can generate even parity bit or I can generate odd parity bit. So there is a IC called 74180. So this is the pin diagram of 74180. So which has got inputs, right, and it has got outputs as well as cascading. Suppose I want to send more information, so more than this inputs, available inputs, then I can cascade, or I can use similar kind of ICs, two or more ICs. I cascade the first IC with the second IC so that I can generate more bits can be sent. So basically this 74180 is called as parity generator as well as checker. So it can be used to detect even or odd parity. So the input bits may have even or odd parity. When the input data has even parity, this particular output will be high. When the input has odd parity, so your output is low. So when the input data has odd parity, the summation of even output is low and this is high. So based on what kind of inputs you are giving to that 74180 IC, that is generator and checker, you are generating the output either high or low. So you have two outputs, one for even output, one for odd output. So based on your inputs, you are going to generate even or odd parity. So for parity generation, parity checking, I will take up an example. So for this example, if I want to generate even parity, if I have 2 bits input, I am going to add additional input called as parity bit. So this 2 inputs, I am going to write 4 combinations, 2 inputs, 4 combinations. So this is an additional bit, parity bit I am going to add to this input. So if I am going to add this as an parity bit as even parity, then here I am going to enter in such a way that I should make it all numbers, it should be even number of ones. So since 0 0, I have to write 0. I have got single one, that is odd number of 1 over here. So I need to put 1 here, so that I should generate even parity, even number of ones. So I am going to add this extra bit so that this entire information should contain even number of ones. So coming to this combination, once again I have got odd number of 1, I am going to add one more bit here, so that this becomes even. So coming to this combination, we have 1 and 1. So 1 and 1, so it is even, so no need of adding 1 here, it is 0, already it is even number of ones. So this is nothing but parity bit. So how do I generate this parity? So wherever ones are there, you can write the equation, you will get A bar B, A complement B, then B complement A. So this is nothing but OR gate. So what I am generating from this truth table, It is nothing but XOR gate. So if I am taking two inputs, right, then I am going to generate two input XOR gate, parity bit considering. So if I am considering 3 bits, so I will be having similarly A XOR B XOR C. So likewise, as number of bits I am going to increase, so will be your XOR gate. So this, whenever I feed the inputs, the output will be either 0 or 1 based on number of ones in at the output side. Suppose you are generating even parity, so your output will be logic 1 when there are even number of, whenever your inputs are odd number, I am going to add even number bit. So it should be even number of ones. So this is how we are going to generate a parity bit, and I am going to check similarly the other side whether it is an even or odd. So this is what regarding parity generator and checker. So this IC accepts the parity 8-bit parity inputs, and it will show whether the inputs are even or odd. So based on the input data, even parity output is I. If it is even parity, the even summation even output is I, else the odd output is low. Let us discuss about comparator. So what is comparator? Comparator is nothing but comparing 2 bits, whether the 2 bits are equal, greater than, less than. It can be 2-bit comparator. If I am comparing 2 bits, it is 2-bit comparator. If I am comparing 4 bits, it will be a 4-bit comparator. So what is a comparator? It is a combinational circuit that compares 2 n-bit numbers in general and activates one of these to 3 outputs, A greater than B or equal to B or less than B. So we have 3 outputs, greater than, equal or less than. So let us take up with an example, 2-bit comparator. So I am going to write here the truth table. In the truth table you can see A and B inputs. So A and B 2 inputs, I will be generating 4 combinations. So 4 combinations, I am going to check 2 bits. If the 2 bits are equal, so these 3 lines are output lines. So we have greater than can be represented as G, equality can be represented as E, less than is represented as L. So if both the inputs are 0, means it is equal, A is equal to B. So my output will be 1 here. So if A is 1, there is a mistake over here, it is 0. So if A is less than B, so my output is 1. If A is greater than B, my output over here is 1. So here A equal to B, my output is 1 here. So finally I will be generating an equation here. Here it is 1 and here it is for greater than, I will get one equation, that is A complement of B. This is not there, it is 0. So coming here A equal to B, it is A complement B complement plus AB. Coming over here we have an equation here 1, logic 1 for this equation is A complement and B. So finally we will end up with 3 equations, one for greater than, one for equality, one for less than. So this is a block diagram of 2 input comparator which checks A and B bits, equality, greater than and less than. So this is the logic circuit. So we have generated 3 equations from this. So it is A complements, I will be using AND gate and OR gate and finally the NOR gate for equality. So for less than, I have got A complement B, it is an AND gate and NOT gate. For equality, I got a 2 AND operation, once again it is XOR, it is given to the input of NOR, so that finally this equation reduces to A is equal to B. And for greater than, once again it is A and B complement. So we get these outputs. So this is the logic circuit of 2-bit comparator, 2 inputs, and we have 3 outputs. So this is the IC 7485 is a comparator which compares 2 4-bit numbers. So now let us discuss what exactly this IC do, the performance or the operation of this IC. You can just see here, this is 7485 IC, it is a 4-bit magnitude comparator. We have A0 to A3, B0 to B3. So we have 4 sets, A with 4 bits, B with 4 bits. This is an additional cascading, this is used for cascading purpose. Whenever I need to increase this, so I can add one more IC and cascade with the first IC. So we have 3 outputs, equality, greater than and less than. So we are going to compare now with each bits. So we are going to compare each bits whether A3 is greater than B3, A3 is less than B3, A3 is equal to B3. So similarly I compare each bit with all 3 expression, that is greater than, less than and equal to. So I am going to compare all 4 bits of A with 4 bits of B by these 3 functions, that is greater than, equality, these 3 operators, greater than, less than and equal to. Based on that, I am going to get my output either high or low. So this is a typical example where they have chosen 4-bit numbers, wherein we are choosing for each, no matter whatever may be the bits, we are first checking with the higher order bit. If the higher order bit is greater than the next order bit, so my output will be greater. So I at greater, you can see greater than, H, L, L, I, H represents logic 1, L represents logic 0. So if my MSB bit is greater than the next coming bits, definitely my output will be greater. So that is how we are going to check for each bits, and the output has been marked over here for greater than, equality and less than. So now let us discuss about an device. It is a memory device where we call it as programmable array logic. So what is programmable array logic? So it is a logic device which consists of set of or array and programmable and array. So what you mean by programmable here? So based on my requirements, I can activate or I can connect that particular AND gate in an array. So we have a set of fixed OR array, fixed in the sense the OR gates are fixed, but AND gate array we can program it, we can connect it based on our requirements. So that is nothing but programmable array logic. So when designing with, it is also called as, it is familiar with, we call this as PAL, PAL. When designing with PAL, the Boolean functions must be simplified to fit into each section. So whenever we are designing any Boolean function, so Boolean function ends up with either SOP or POS. This SOP or POS can be connected or done simplified using this PAL function. So a product term cannot be shared among 2 or more OR gates. So this has to be taken into consideration while designing PAL. So therefore each function can be simplified by itself without regard to common product terms. So we should not share one product term to two or more OR gates. Care should be taken while designing this. The output terminals are driven by buffers. So output of this PAL device is connected to buffer. We will take up an example how we are implementing the functions using PAL. So we will take up 4 functions. The first function W, X, Y, Z. W, X, Y, Z, 4 functions. So you can see the summation 2, 12, 13 for first function, second function listed with min terms, third function listed with min terms, similarly fourth function. So we'll apply this in truth table, 4 variable truth table. Finally, we simplify the functions. We end up with this equation A, B, C complement, A complement, B complement, C and D complement. So once I simplify, we will get this simplified equation. So similarly for X, we get this equation. Similarly for Y, we get this equation. Z, this equation. You can note down this Z has got 4 terms. Out of these 4 terms, these 2 terms are similar to the first function. It has got same. So I can replace these 2 terms by W. This is how I am going to reduce my number of gates. So this is basically a design, programmable logic. So this is how we are going to replace 2 product terms by a single, the 2 terms we are already there in one function. So I am going to reduce this out of 4 terms to 3 terms, which is connected once again back here. So this, note that this equations are generated by entering these variables in K-map, and after reducing we will get this equation. So K-map reduction, you got the simplified equation. Once you get the final simplified equation, I am going to write this equation, program this equation using programmable array logic. So we have 4 functions. Each functions once again is with product and OR term. So Z has 4 product terms. We have replaced by W with 2 product terms. This will reduce the number of terms for Z from 4 to 3. So you can just see in the table, we have A, B, C, D, the variables. So for the first function, we got this equation. So A, B complement. So A, B complement. I am going to write this. These are the AND inputs. A, B, C complement, and A complement, B complement, C and D complement. So these are the AND inputs to W function. So I have written the AND inputs here with 3 variables, here 4 variables. This represents the first function. So second function, I have A plus B, C, D. So I have only one variable here, and in the second gate, AND gate, I am having 3 variables here. So the rest is written as dash. So coming to third variable, we have 3 AND gates with A complement and B, A complement and B, and C and D. You have B complement and D complement. So we are generating here 3 product terms. So coming to Z. So as we have discussed in the previous, so the Z has got a common term as W. So I can replace these 2 terms as W here. So I have reduced 4 terms to 3 terms by writing as W. So we have written the one term as W. Under W it is 1. We have one product term here, A, C complement, G complement, and another product term A complement, B complement, C complement and D. So this will be an AND inputs of programmable array logic. So this is the table what we have generated from the equation. So you can just see here, So we have AND gates inputs. So these are the product terms. So we have generated, you can see the array. Why we call it as array? We have a set of AND gates here. These are the product terms. Product terms. You can just see the product terms. This is negation of it whenever negation is required. So AND gate inputs. So inputs product terms and AND gate inputs. So this is programmable array logic implementation. So AND and OR gate. So this is connected to particular gates. So you can see here AND gate inputs A, B, C, D and W, and the product terms 1, 2, here the product terms. It's connected to 1, 2 and it is connected to 4. So likewise we need this product terms and all terms are connected. So this is connected in a form of an array. So let us discuss programmable logic array, which is a kind of, once again, a logic device used to implement combinational logic circuits as we did in PAL. So it has a set of programmable AND gate planes and which links to a set of programmable OR gate planes. So we have AND planes, also OR planes, and we have 2 to the power of n AND gates for n input variables. For m outputs, PLA there should be m OR gates, each programmable inputs from all of this AND gates. So you can just see here, if we have 3 variables, we have taken 3 variables, normal variable, and this is a complemented variable, C complement, B complement. So we have connected here, you can just see here, A complement and A, B complement and B, C and C complement. All the normal inputs as well as complemented inputs are connected to this gate, AND gate. Similarly, we are connecting all combinations here, set of AND gates. So whenever according to the functions requirement, so your output, I am going to fuse or I am going to connect to this particular AND gate. So this particular AND gate, so this OR gate consists of so many inputs. So if I fuse, if I make connection over here, so only particular this output will be connected to this OR gate. So if you fuse or if you blow here, so only this AND gate is connected. If I connect this more than one AND gate, so both will be ORed here. So this is how we can generate a logical expression using an programmable logical array. Take an example here, PLA logic implementation. Suppose we have multiple functions like this, F1 to F6. So we have F1 with one function, F1 is a function with one term A, B, C, F2 with 3 terms. So how we can generate all of this function using PLA? Need not connect a single circuit for all this function. All these functions can be generated using single PLA logic. So since we have 3 variables, all the 3 variables with the complemented inputs are connected. So input is an AND array and output is a OR array. So you can just see, I can generate as many functions I want by connecting output OR gate. So F1, the equation is ABC. So there is a line over here which is connecting, F1 is connecting for all AND gates. Wherever required, I am going to fuse or blow this. So there is a connection between this F1 and your A, B and C. So this cross represents connectivity. So this is the fuse is blown here. So this particular connection has been made for F1. For F2 similarly, I just want A, B and C. So I can get A here, B here and C here. So all three are taken, are blown here to get F2. So coming to F3 similarly, A, B, C. Here it is E. Note that A, B and C. Here also A, B and C. So we are connecting the particular, there is a intersection between and or this particular connectivity is done to get this particular function A, B, C. So this you are going to generate A, B, C. So similarly here I can get A complement, B complement, C complement. So for F4 once again I can get my output. So based on different functions, the equations, I can fuse or I can blow this and OR array intersection. So this is, there is a set of OR and OR plane where you are generating the functions. This is how we are going to implement a logic, Boolean logical expression using PLA. So what is the difference between PAL and PLA? So PLA has both programmable and OR planes, whereas PAL has only programmable and planes and OR plane is fixed. So I can change in PLA, I can program and as well as OR, set of planes, and planes and OR planes, I can change both. I can program it, change in the sense I can program. In PAL, I can only program and plane, but OR plane is fixed. So PLA has more flexibility in the logic circuit function implementation than PAL because it is both programmable. Since it is AND plane and OR plane both are programmable, so it has got more flexibility over PAL. So PAL is simpler to manufacture than PLA because of course OR plane is fixed, so that's why it is simpler. So PLA has reduced speed performance. Since you are programming both the planes, the speed matters over here. PAL devices are manufactured in smaller size compared to PLA. So this is what we are comparing, PAL and PLA, both are programmable and an OR array. So only the difference over here is programming planes and fixed planes. So either the and OR both are programmed here, or in PAL AND gate is programmed, it is programmable, OR plane is fixed. So it is PAL and PLA is also called as memory device. So it is nothing but you are going to reduce the number of circuits by using PAL and PLA. You can realize more functions using this PALS. So let us discuss now the arithmetic building blocks. So we are doing certain arithmetic operations. How these operations are performed inside the system. So we are going to design the circuit for the arithmetic operations. So the basic arithmetic operation we are going to talk about is adder. So under adder is nothing but an operation which you perform addition between numbers. So let us discuss off adder. So what is off adder? It has got 2 inputs and 2 outputs. Inputs are, let us say inputs are A and B, and the outputs are named as sum and carry. So we are going to generate once again truth table by taking 2 inputs, and of course 2 inputs I am going to generate 4 different combinations, and we have 2 outputs here. While after adding we get sum as well as we get carry over here. So I am going to write truth table for this. So it's a binary addition what we are doing. So 2 inputs, 2 outputs. One output is sum, where we are going to get when we add 2 numbers, digits. So then if at all and there is carry, then the particular bit is I. Suppose if I add 2 binary zeros, so the sum is 0, carry is 0. Suppose I add 0 and 1, my sum is 1 and there is no carry, so that's why I have written 0 here. So when I add 1 and 0, it is same, the sum is 1 and carry is 0. So now I am going to add these two, 1 plus 1, it is always 0 and 1. So it is in binary, it is 2, 1 plus 1 it is 2, the 2 in binary I write it as 0, 1. So the sum is 0, carry is 1. So we get 2 outputs. So while seeing this output, you can just see once again I write an logic equation wherever there is output 1. So the output 1 over here is, the logic equation is a complement b plus a b complement. So I have got 2 outputs as logic I. So I will be getting an equation with 2 terms. The first term is a complement b, the second and plus b complement a. So a complement b plus b complement a is nothing but XOR gate. So as we have discussed in the previous session, so I will get an output sum when I XOR 2 inputs, that is a and b. So my sum is generated using XOR gate. How the carry is generated? You just see over here, logic 1 is here, the inputs are I here, both I. So it is a and b, it is one term, that is product term. So carry is generated here using AND gate. There is one XOR and one AND gate. So carry is generated a and b. The equation is for carry is AB. The equation for sum is a complement b plus b complement a. So that is a XOR b. So finally I write an equation. Then I develop a logic circuit which produces 2 outputs, sum and carry. Whenever I give, let us check this circuit. Whenever I give the input as 0, 0, input to XOR gate, here it is 0 and 0. If both inputs are 0 to the XOR gate, my output will be 0. So if any one of the input to AND gate is 0, my output is also 0. This is how I am going to verify the truth table from this circuit. Suppose I take up an example 1 and 1. So if I give 1 and 1 here, so 1 here, 1 here, if both inputs are I to the XOR gate, my output is 0. If 1 and 1 to the AND gate, both the inputs are I, my output is 1. So you are going to get output as 0 and 1. So this is a circuit diagram for half adder and truth table for half adder. Similarly, I can build full adder circuit. I can realize this circuit by taking into 3 variables. So as usual, we have 2 inputs in half adder. We are going to add additional input, the third input, that is called as carry in. It is also designated as C in. The output is designated as C out, or I can write carry and sum. So out of these 3 inputs, I am going to generate 8 combinations. So similarly, I am going to add 3 bits now, as we did for 2 bits. Now we are adding for 3 bits and generating sum and carry. So note that this is binary addition. So when I add 2 numbers, I am going to generate sum and carry. So finally I take up these 2 outputs, that is sum and this is carry. So when I write, I'll enter this in K-map and I'll get the equation for sum and carry. So let us solve how we get the equation, what is the equation that I am going to get in sum for sum and for carry. So let us solve this. So we have 3 inputs, we have sum, we have carry. So I am going to take all combinations. Since 3 inputs, I'm taking all 2 power 3, 8 combinations. Now I am going to write the sum and carry for each of this combination. So when I add all 3, it is 0. So when I add this 2, sum is 1, carry is 0. Similarly over here, then here it is 0 1. Since 1 1 means it is 0 1. Once again we have 1 0 here. So 0 1. So 0 1. Here it is 1 1. So here take up this as an output sum. So wherever logic 1 is there, I am going to take this equation terms. I am going to generate an equation. Either I can reduce this equation using K-map, or I can reduce this equation using Boolean law. So if I am taking K-map, I will be taking 3 variable K-map. So 3 variable K-map, I have A, B, C. So this is the 3 variable K-map. So I am going to enter this once in that particular cell. So this is cell number 0, 1, 2, 3, 4, 5, 6, 7. These are the cell numbers. So for the cell number 1, cell number 2, cell number 4 and cell number 7, I am going to enter 1 here. So cell number 1, cell number 2, cell number 4 and cell number 7. So these are the logic ones I have entered inside the K-map. So since it is not adjacent, I can't group this. So it will be a single terms. So finally I will end up with 4 terms. So how to write these terms? So if you can see here, it is this way. It is A complement, B complement, C plus similarly A complement, B, C complement. So A, B complement, C complement plus A, B, C. So I will get this equation from this K-map. So finally I am going to reduce this expression using Boolean law. So I will take a common term here. So A bar B plus A here it is C. These 2 terms we have C complement common. I will get this equation. So for this, once again C is complement, so I will get this equation. So finally these 2 are common. So I will end up with A XOR B XOR C. This is nothing but I can take this as one term, this is complement and one term, this is normal and another term. So this becomes once again an XOR term. So finally I will end up the sum equation with A XOR B XOR C. So if I take up carry, similarly if I do carry, write in K-map. So you can just see the cell number 3, then 5, 6, 7, 5, 6, 7. Now I can, there is an adjacent ones placed in the cell, I can do grouping. So the grouping is done this way. I will end up with 3 terms. So you will get 3 terms here. So you can see C is equal to, this is common, it is BC, and over here it is A and C. Over here it is A and B. So this is the final equation for carry. So we have 3 product terms and 1 sum term. So to take together, we have an XOR operation for sum and product terms for carry. You can just see here A XOR B XOR C, A XOR B and C, you will get sum. So you can see for carry out, product terms are there. So I will be taking this product. This is how I am going to generate sum and carry outputs for full adder. So half adder and full adder, it's basically designed for addition of 2-bit numbers and 3-bit numbers. So similarly, I can generate the circuits for more number of bits by adding inputs and then reducing the equation, finally drawing a circuit. So with that, we are going to design an ALU. So what is an ALU? It's an arithmetic logic unit, which is basically a major component in CPU of a computers. So what is the operation performed by ALU? It does logical operations like AND, OR, NOT, XOR and NOT, NAND operations. It can do bit shifting operations, either I can shift the position bits right or left. Suppose basically the shift operation is done for multiplication operation. Then arithmetic operation like addition, subtraction, division can be performed using this arithmetic logic unit. So this ALU does all these operations, logical operations, shifting operations and arithmetic operations. So additions can be used to substitute for multiplication. We have a circuit for, we don't have separate circuit for multiplication. It is a repeated addition is done for multiplication operations. So you can just see the functional representation of ALU. So the ALU consists of, you can see the inputs A0, A1, B1, B2, B3, S3, S1, S0, and we have the functions here. So we have the mode control here, M is equal to 1, M is equal to 0. If my Cin is equal to 1 or my Cin is equal to 0, it is nothing but if my carry input is 1, what is the operations that I can perform, and carry input is 0, what operations I can perform. We have 2 mode controls here, mode 1 and mode 0. So various operations can be performed using this ALU. So we have got these 4 inputs. So either I can do additional operation, NOT operation, XOR operation, shifting operations. So 74181 is an IC, medium scale integration TTL circuit with 75 logic gates and 24 pins. It's a 4-bit wide ALU that can perform all traditional operations like add, subtract, decrement with and without carry, as well as AND, NOR, XOR, shifting operation. Specifically, we can't do multiply and divide functions using this IC. We use shift and add for this operation, addition operations. Shift is not an explicit function here, but can be derived from several available functions, including A plus B plus A. So we can implement such functions using this 74181. So these are the operations I can perform. So suppose I consider A and B are the variables. So I can perform XNOR operation OR operation, then after I can do multiplication operation here. So, these are the mode controls. With this mode control we can perform all logical, arithmetic, bitwise operations using 74181. With this I conclude the data processing circuits, operations, the designs. It's very important, which is need for many applications. So, this designing basically helps you to build a circuit which helps in communication fields. Thank you.